For most of the 20th century, global timekeeping was entirely dominated by the Swiss. They built an absolute monopoly on a foundation of intricate, manual labor, relying on centuries of tradition to assemble microscopic springs and gears by hand. But relying on physical momentum creates an unavoidable speed limit. Inside those watches, a mechanical balance wheel swings back and forth at a relatively slow rate of about 2.5 times per second. That slow rhythm makes it highly susceptible to gravity, temperature, and motion, causing the watch to lose anywhere from several seconds to minutes every single day. Engineers tried to squeeze more accuracy out of the format in the 1950s and 60s by introducing battery-powered stopgaps. The Bulova Accutron replaced the traditional mainspring with a tuning fork that vibrated at 360 Hz, offering much better daily precision. Yet these stopgaps still drove their hands using vulnerable physical gear trains. Hitting the ultimate limits of precision meant abandoning physical momentum entirely, jumping straight into solid-state electronics. That leap didn't happen in the valleys of Switzerland. It happened in the rapid technology and electronics boom of 1960s Japan. After years of trying to shrink massive laboratory equipment into a wearable format, a Japanese firm called Seiko reached the finish line. On Christmas Day, 1969, they unveiled the Quartz Astron, the world's first electronic quartz wristwatch. This bar chart illustrates the severity of the gap between the two technologies. While a standard mechanical watch of the era drifted by several seconds every day, the Astron drifted by roughly 5 seconds over an entire month. European watchmakers had spent generations painstakingly refining their springs and gears. A single electronic circuit now outperformed their best manual labor by a factor of 100. The origin of this technology dates back to 1927, when Bell Labs researchers Warren Marrison and J.W. Horton built the world's first quartz crystal clock. It was an enormous, room-sized apparatus, but it proved a vital concept. Looking at this microscopic cross-section, we can see a scientific property called piezoelectricity at work. When you pass an electrical voltage through a piece of quartz, the crystal physically deforms. As it flexes back, it generates its own return electrical voltage. If you cut that quartz into a very specific tuning fork shape, it forces the crystal to vibrate at a blistering, highly stable rate of exactly 32,768 times per second. Because of the crystal's rigid atomic lattice, this vibration is completely immune to normal shocks or temperature swings. By running a tiny current from a watch battery into that crystal, engineers turned a naturally occurring rock into a perfectly consistent, unbreakable metronome. The engineering challenge of the 1960s was figuring out how to take those room-sized, temperature-controlled oscillators and shrink them down into a low-power module that could fit on a wrist. This flow diagram outlines how a microchip handles that blistering frequency. A quartz watch uses binary logic gates to mathematically divide the 32,768 Hz input strictly in halves. It divides by 2 15 times in a row until the frequency steps all the way down to a perfectly exact single 1 Hz pulse. That single electronic pulse is then fed into a tiny component called a Levet stepping motor. The pulse creates a brief magnetic field in a coil, which forces a miniature rotor forward, physically advancing the watch's gear train exactly 1 second. Timekeeping had moved past measuring physical momentum. It became an exercise in mathematical division. Because this new timekeeping relied on integrated circuits rather than intricate mechanical parts, Asian and American factories could mass-produce the modules for pennies. Automated assembly lines rapidly replaced the need for skilled manual labor. This descending graph tracks the Quartz Crisis. With global markets flooded by cheap, highly accurate digital and analog watches, the Swiss mechanical watch industry fractured. Between 1970 and 1983, the number of active Swiss watchmakers plunged from roughly 1,600 down to 600. The Swiss establishment had initially dismissed the complete value of solid-state electronics, choosing to protect their legacy mechanical business model. That single refusal nearly destroyed their centuries-old global monopoly. To survive, the remaining Swiss firms executed a desperate pivot. Led by executives like Nicholas Hayek, they quickly merged their resources and adopted the very technology that nearly killed them. They created Swatch, producing thin, automated, plastic-cased quartz watches to win back the entry-level market share. Simultaneously, the industry reframed the mechanical watch entirely. Since a mechanical gear train was no longer a practical necessity for telling time, Swiss brands marketed it as a display of heritage, repositioning the mechanical watch as luxury art. The quartz crystal made ultimate precision completely accessible to the masses. Today, that identical piezoelectric science is the invisible heartbeat of modern infrastructure, regulating everything from your digital watch to GPS satellites orbiting the Earth.